Hi everyone, this is Kalyan Kumar here and welcome once again to Chemistry Universe. We've already done 3 lessons of organic chemistry. We have done IUPAC nomenclature, we've done general organic chemistry, we have done isomerism, and in this lesson, we are going to talk about alkyl halides and aryl halides. Now, alkyl halides, this particular lesson is very important from the point of view of reactions. The first time we're going to introduce reactions in this lesson. So far, we have done general concepts, we have done naming, we have done various types of isomerisms. There were no reactions involved. Now we're going to talk about reactions and reaction mechanisms. That is going to be very, very important. And in this particular part, I'm going to talk about the nature of solvent and the various types of kinetics that are involved in the particular reactions that we're going to learn. So this is a very important lesson from the point of view of the mechanisms and how we use the concepts we've learned in understanding reactions. So let's begin with alkyl halides and aryl halides, part 1. And in this one, we talk about the types of solvents and kinetics of reactions. So let's begin. Now, when it comes to the various types of solvents, there are basically 2 types. Solvents can be categorized basically as 2 types. One set as the polar solvents, and obviously the other set has to be the non-polar solvents. And how do we distinguish between them? Well, polar solvents, as you can understand, are the ones which do not have the net dipole moment equal to 0, or which have a net dipole moment. Whereas non-polar solvents like CCl4, like benzene, their net dipole moment is 0, and they are the non-polar solvents. Now, polar solvents, on the other hand, are of 2 types. Two types of polar solvents. We have the first variety, which is the polar protic solvents, and the next variety is the polar aprotic solvents. Now, as the name itself suggests, the polar protic ones are the ones in which the solvent has a hydrogen atom attached to a highly electronegative element like N over F, and which is acidic enough to solvate anions. Whereas the polar aprotic solvents are the ones which have net dipole moment not equal to 0 but do not have any acidic H. So the presence of acidic H is what distinguishes a polar protic from a polar aprotic solvent. So let's talk about the polar protic solvents. Solvents that are capable of donating H plus ions, or solvents in which H atom is connected to a highly electronegative element. Examples are water, ethanol, carboxylic acid, ammonia, etc. And in all of them, you will notice one very important thing, and that is that they all have acidic hydrogen. For example, H2O. Now, when I say H2O, you have the O attached to H. Now, even though this is very weakly acidic, in fact, water is neutral, but the fact of the matter is that the hydrogen is attached to a highly electronegative element like O, which means it can come off as H+. So that is pretty important when it comes to polar protic solvents. The next is the polar aprotic solvents, and these are the solvents that are not capable of donating H plus ions, or solvents in which the H atom is not connected to a highly electronegative element. And the examples of this include the diethyl ether, all solvents which don't have the net dipole moment as 0, but yet are not able to give any H because the H is not attached to a highly electronegative element like N over F. We have another form of ether that is called THF, or tetrahydrofuran. You got to remember the names of these and the formulae. Very commonly used solvent is acetone, again polar aprotic. You have dimethyl sulfoxide, or also known as DMSO. You have dimethyl formamide, called DMF. You have dimethyl acetamide or DMA. You have dioxane, a diether, cyclic diether. You have dichloromethane, and you have crown ethers. There are various types of crown ethers. And then you have HMPT, also known as hexamethyl phosphorus triamide, HMPT, and its oxide called the hexamethyl phosphoramide or HMPA. So you got to remember the names and the formulae. Now let's understand the role of solvents. Now the role of solvents, well, non-polar solvents do not solvate or stabilize either cation or anion. Again, there is a spelling error here. It's solvate. And they do not solvate cations or anions. These are the non-polar solvents. Their role is very passive. Their role is only to dissolve the solute. They neither hinder nor assist in any particular reaction. On the other hand, the polar protic solvents end up solvating both the cation and the anion. Say for example, water. So when you dissolve NaCl in water, the Na plus ions get solvated by the O of the water. Though I've shown the number of O's as 6, but remember it can always vary. And the Cl minus ions are being solvated by the acidic H present in water. Whereas when you take an aprotic solvent, a polar aprotic, it will only solvate the cation, not the anion, because it doesn't have an H that is attached to a highly electronegative element. And therefore, Na plus gets solvated by the O in the case of acetone, but there is no H that is capable of solvating the Cl minus. So whenever an anion is solvated or trapped, its reactivity decreases. So reactivity of an anion in polar aprotic solvent is always greater than in polar protic solvents. Now try and understand this importantly. The fact is, the cations get solvated, but the anions are free in an aprotic solvent. So anions can react easily. Whereas in the case of polar protic solvents, the anions also get solvated and their reactivity is going to decrease. So kinetics of reaction. Now let's talk about the kinetics. Now for a reaction of the type Ma plus Nb giving products, the rate of the reaction is given by rate equal to Ka to the power x b to the power y. Now this x and y, they are experimentally determined. Now one might wonder, why is it that in the reaction kinetics, why is it that the rate is proportional to the concentration of reactants in the first place? Well, the simple reason for that is the fact that collisions are the reasons why reactions happen. I think we can clearly understand that. So collisions are the reason why reactions happen. So if you say, for example, 1A is colliding with 1B to give a product, the moment I double the concentration of A, the probability of collision of B with A doubles. In the same amount of time that it was colliding previously, it will have double the chance of colliding with A. So the moment you increase the concentration of A, the probability of collision with B increases. And when you do it, when you double B instead, the same thing happens. The probability of A colliding with B doubles because there are more B now. So as concentration increases, rate will increase, which is why rate is proportional to concentration. Of course, the power to which it is raised to the concentration can take any value, but it is proportional to it. So that is pretty important to understand. So where X and Y are called order of the reaction with respect to A and B respectively, and X may or may not be equal to M and Y may or may not be equal to N, K is called the rate constant or the velocity constant and represents the value of the rate when all reactants are at a concentration of 1 mole per liter. Now try to get this. Rate is K, A to the power X, B to the power Y. So what is K? K is equal to the rate when A is 1 and B is 1 molar. So rate constant or velocity constant is the actual rate of the reaction when each reactant is at unit concentration. And when they are not at unit concentration, then it is proportional to concentration of A to the power X and B to the power Y, multiplied of course by the value when both of them are 1, which is K, rate constant, also known as velocity constant. Now the parts X and Y are called order of the reaction. X is the order with respect to A, Y is the order with respect to B, and they may or may not be equal to the stoichiometric coefficients of A and B in the actual reaction. So let's find out when they are equal and when they are not. So if the above reaction is elementary, that is occurring in one step, then the value of M will be equal to X and the value of N will be equal to Y. But if the above reaction is not elementary, that is does not occur in one step, then the value of M may or may not be equal to X, N may or may not be equal to Y. Again, this is pretty important for you to understand. Why is this so? Well, when the reaction is elementary, A plus B giving something, then obviously A and B are colliding. And the coefficient of A is, let's say, is 1 and the coefficient of B, let's say, is 2, or perhaps even that is 1. Then the power and the coefficients will match. Why? Because on doubling A, since it is one single step, all the collisions that are determining the reaction are happening in that very step. So when you double A, the probability of collision doubles. Instead, if you double B, the probability of collision again doubles. And if you double both, the probability of collision becomes 4 times. Because now you have A1 and A2, now you have B1 and B2, and you have that many combinations to play with. So the probability of collision determines the order. So more the probability, more would be the order. And in this case, if it is a simple reaction, one-step reaction, all collisions are happening within that reaction, or you can say that all collisions that determine the rate of the reaction are happening in that very step, and therefore the power and the coefficients match. But if the reaction occurs in multiple steps, then it is said that the rate of the slowest step is what determines the rate of the reaction. Why is that? Let's take an example. Let's take an example of, let's say you are studying physics, chemistry and math. Maybe you're preparing for an entrance exam like IIT-JEE. So you're studying physics, chemistry and mathematics. And when you're studying this, let's say that physics takes 3 weeks to complete. The entire syllabus gets completed in 3 weeks. I'm just asking you to imagine this. And let's say maths takes 1 month to complete. And let's take chemistry takes 2 years to complete. When is your exam preparation complete for all subjects? When will you be able to write the exam? Only after 2 years. Despite one taking 3 weeks, the other taking 1 month, and chemistry taking 2 years, it will take 2 years for you to complete the syllabus because chemistry is the rate determining step. It is the slowest step. So the slowest step determines the rate of the reaction. Now this is when all the 3 reactions are happening simultaneously. But if the reactions were to happen one after the other, first physics is over in 3 weeks, then math is over in 1 month, then chemistry is over in 2 years. So actual time taken is 2 years, 1 month and 3 weeks. But isn't it possible to say approximately 2 years? I mean, you're not exactly going to count the number of days or the months. You simply count the number of years. So when one step is extremely slow compared to the other, then the rate of the overall reaction can be approximated with the rate of the slowest step. Now, if a reaction occurs in multiple steps, then it is assumed that the rate of the overall reaction is equal to the rate of the slowest step, also called the RDS, rate determining step, assuming that there is one slower step and it is much slower than the other steps. The value of X and Y are determined experimentally, that I've already told you. Now, for a single step reaction, the sum of the stoichiometric coefficients of the reaction is called molecularity of the reaction. Again, a very important thing to understand. So, if you have a reaction and the number of reactant molecules in the rate determining step are known as molecularity of the reaction. The molecularity of the reaction tells you that in the most important step that determines the rate of the reaction, how many molecules are involved. And it is said that the molecularity of any reaction can never be more than 3. In fact, even 3 is rare, but it can never be more than 3. Because since each of the steps are occurring by single steps at least, see, if a reaction occurs in 4 steps, and let's say the third step is RDS, each of those steps are single steps, right? So in the RDS, whatever collisions are occurring, those are the collisions that are leading to the product of that step. And that is a rate determining step. Now, to expect more than 3 molecules to hit at the same moment, the probability is extremely low. See, even when you have an accident, a car accident, at one point of impact, only 2 vehicles will be involved. 3 vehicular collisions are rare. 4 is even rarer. So, what we say is that the molecularity of the reaction does not exist, does not become more than 3. Okay? So, maximum molecularity you can ever achieve is 3. And for a multi-step reaction, the sum of the stoichiometric coefficients of the reactants in the RDS is called molecularity of the reaction. And for a single step, that itself is the molecularity. And remember, the molecularity can never be greater than 3, cannot exceed 3. Now let's understand a concept of activation energy. Now consider the following reaction profile. We've already done reaction profiles, if you remember, in GOC. And let us say this is a free energy on the y-axis and the progress of the reaction on the x-axis. And this is the way the reaction is happening, the energy profile. And we already talked about how the energy profile works. It is basically a theoretical concept, and this concept is basically done using computer software. We feed in all the information. We feed in what the energy, the free energy of a reactant is. We feed in what is the free energy of the product is. And then the program itself takes us through the entire profile. So this is a theoretical graph that has been made. So this particular graph is determining how the energy of the system is going. Now, if you notice, there's something called a transition state, and we have already talked about that. The energy difference between the reactant and the transition state is called activation energy. This means this is the minimum energy which the reactants at that particular temperature need to get to reach the TS. Once they reach the TS, they can always come down on their own. Energy can decrease in any system, natural system, on its own. The increase has to be artificial. So you have to provide that. Let's assume a particular reaction in which, let's say, I have a wall with a hole big enough for a tennis ball to pass through, and there's one guy throwing a lot of tennis balls through the hole from across the room. Now, for the tennis ball to pass through the hole, don't you think he needs to send the tennis ball by a certain minimum force, certain minimum energy, so that it can cross the hole? Now, it may be properly oriented, but if the energy is not sufficient, it will just fall short of the hole. That minimum energy through which the ball has to be thrown so that it can pass through the hole, in that case is called the activation energy. So, in this case, in every chemical reaction, whether exo or endothermic, energy will always have to be given first to the reactants so that they can reach the TS. And remember, this is free energy graph that you're seeing. The minimum energy required to take the reaction to TS is called activation energy, EA. So basically, I'll repeat the graph, and this energy gap is activation energy, and this will come very handy for us. Lower the value of EA, faster will be the reaction, because less energy it needs quickly will happen. Free radical reactions and some radioactive reactions are the ones which don't require activation energy. They happen without any activation energy. They will directly go from reactant to product on their own. The moment you put them together, they will happen. But for all the reactants, some energy has to be supplied. And one of the relationships between activation energy and rate constant is given by the relation K equals A e to the power minus EA by RT. We'll discuss more about how these laws are derived and what do they actually mean in detail when we do chemical kinetics. But this is the background of chemical kinetics you need. And if you look at that particular thing, you will notice that K is A e to the power minus A by RT, and this EA, if it is low, then minus EA by RT. Now EA by RT will become high. Sorry. If this EA is low, EA by RT will become low. But since it is negative, negative EA by RT will become high. And e to the power anything which is increasing will always increase the overall value, and K will increase. Which is why lower the value of EA, faster the rate of reaction, because greater is the value of K. So that brings us to the end of this particular lesson. I hope you were able to understand the concept that we talked about here. And I also hope that if need be, go through this lesson again, go through this video again. And if you have any doubts, any queries, any questions you want to ask, put them in the comment section below. And if you like these videos, like these sort of chemistry tutorial videos, please do subscribe to this channel. And if you like this particular one, do hit the bell icon and ensure that you share this with your friends who would also benefit from the same. With that, this is Kalyan Kumar wrapping up this video. Thanks for watching. Have a great and a safe day. Bye-bye.